In this video, we're going to revisit a problem that I had previously started solving algebraically, and hopefully you'll see that the graphical method can be much simpler and faster in solving these repetitive equations. So go ahead and pause the video now just to read this problem statement again, get reoriented to the problem. And I've already copied the process flow diagram that we had from last time. And also remember that I've solved with an overall material balance what D, the distillate flow rate, and B, the bottoms flow rate are. I can't do that part graphically. So because I'm given what both compositions are, I'm just setting up an overall material balance to solve for D and B. Then the other thing that's weird about this problem is that I said in a previous video that there were three types of problems: the design type problem, the evaluate type problem, and the predict type problem based on what is given. And for this particular problem, this is not any one of those three. So this problem is actually overspecified and it ends up working out. But I've actually given you more information than you need in order to be able to solve. So in other words, I know what end stages are. I know what the feed stage is. I know what the reflux ratio is. And I know what the relative volatility is and what the compositions are. So I'm given a lot of information. It's neither one of those, but it's still, this problem works out. I chose the numbers such that the information is consistent. So I'm already given what the reflux ratio is. At this point, we could go through and plot what our rectifying section operating line is. Remember that the RSOL, rectifying section operating line, is y of n plus 1 is equal to r over r plus 1 times xn plus 1 over r plus 1 times xd. All right, and because we're given what xd and r are, we can solve. So 10 over 11 times xn plus 1 over 11 times 0.80. That is an equation that is in linear form already that we can plot. So option one, remember, you just have to know a point on the line and the slope of the line. You could plot it. So I could plot what the y-intercept is and then plot what the slope is. In fact, if I were doing this on a computer, on Microsoft Excel, this would probably be the easiest way to plot the rectifying section operating line. But if I'm plotting it by hand, I'm going to show you a quick trick that you can use to make this plotting go a little bit faster. And this is a similar trick to the one that I used in the single stage equilibrium stage. So I know that if I plot y of n plus 1 for xn equals xd, I have a simplifying case. So if I plug in xd, I'm going to get r over r plus 1 times xd plus 1 over r plus 1 times xd. The xd's are going to cancel out. I'm going to get an r plus 1 in the numerator. That is going to cancel with the r plus 1 in the denominator, and it's going to equal simply xd. So this tells me that for all rectifying section operating lines, the point where xd is on the y equals x line must be on the operating line, where xd is on the y equals x line is also on the operating line. So instead of, once again, plotting what the y-intercept is, 0.8 divided by 11 is 0.07, around that or so. So it'd be around here. So I could plot this point and then plot a line of slope 10 over 11. Or I know that this is a point that's on the operating line as well. So following 0.8 all the way up till there. All right, and then I'm going to try and use the ruler. Okay, I tried to plot this for a while on the Surface Pro. It's not on OneNote. It's not letting me get the exact precision that I need. But if I were doing this by hand with graph paper, I would use the slope of 10 over 11 to plot the rise over the run. So the rise is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the run is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm actually pretty close. That's not too bad. All right, so this is going to be my RSOL. Notice that it is also going through, oh no, undo. It's also going through the y-intercept. So the actual y-intercept, I just calculated it, is supposed to be 0.072. I'm off a little bit, but I'm going to be comfortable enough because, like I said, the precision is difficult to achieve on the Surface Pro. Next, let's plot the SSOL. And remember, the stripping section operating line had a equation of y of n plus 1 is equal to VB plus 1 over VB times xn minus 1 over VB xb. Now, when I derived it above, I had y of n and x of n minus 1. It's going to work out the same way. It just is happening with what indice you're using. So if it's n is equal to 6, it's going to be the same as if n is equal to 7. So these are equivalent. And I could do a similar thing here, except the problem is I don't know what the boil-up ratio is quite yet, but I can work it out algebraically. So before I continue along this path, I need to calculate what the boil-up ratio is. I know from above that the reflux ratio is 10, and that is equal to L over D, more specifically L0 over D, where L0 is the flow rate of the reflux stream. Therefore, L0 is equal to L, which is equal to 306. All right, so the liquid flow rate in the rectifying section of the column is equal to 306. Now, my problem statement says I have a saturated liquid feed, so that corresponds to Q is equal to 1. And I can use the equation that I derived above, or I could just simply think about it. If I'm adding a saturated liquid feed, that is going to add to the liquid flowing downwards. So L prime in this case is going to be equal to L plus F. And it's only this equation because the feed is saturated liquid. If the feed was saturated vapor, I could not write this equation. But I know that the feed is 100, L is 306, so therefore L prime must be 406 moles per second. Now, V prime is unaffected by the feed, so V prime is going to be equal to V in this case. And I think I'd calculated this before, in the video before, algebraically. It should be 306 plus 30.6. So it should be 336.6. And the boil-up ratio, VB, is equal to V prime over B, or 336.6 divided by 69.4. All right, and algebraically that works out to 4.85 is my boil-up ratio, about. So therefore I can plug in my VB and my XB, and I could obtain an equation for the slope of the operating line. So 5.85 over 4.85 xn minus 1 over 4.85 xb, where xb is 0.08. Now I can do a similar thing here where I can simplify my life a little bit by plotting a different thing than the y-intercept. So I can say that y of n plus 1 for xn is equal to xb is equal to vb plus 1 over vb times xb minus 1 over vb xb. xb's are going to cancel out again. My 1's are going to cancel out. vb over vb is equal to 1. This is equal to xb. So this, an analogous statement, means that the point where xb is on the y equals x line is on the stripping section operating line. Let's go ahead and write that in. So 0.08 is there. And then I'm cheating a little bit because it's hard to draw a line of slope 5.85 over 4.85. This is approximately 1.2, but I know where it's supposed to be. So again, this is going to be difficult if I try to plot this by hand because I can't accurately count fractions of a square. So I'm just going to do a little trick, draw it in, and then I'll show you how I knew that a little bit later. Okay, a slope of 1.2 should correspond to about 6 over 5, right? So if I count 5 squares over, 1, 2, 3, 4, 5, and 6 squares up, 1, 2, 3, 4, 5, 6. Again, I'm pretty close, right? So that slope is accurate. Now I'm going to explain how I knew that that was the slope without being more precise about how I was calculating it. And it is because I know that the third operating line is not independent of the other two. So the last operating line that I can draw is the feed operating line, which has an equation that I derived before. And if I plug in my Q value, I'm going to get that the slope is undefined. and it doesn't have a y-intercept. So instead of using the y-intercept to plot this, because I can't, because there is no y-intercept, we're going to use the same trick and say that y of n plus 1, where xn is equal to z, is going to be equal to z. So if I plug in q over q minus 1 times z minus z over q minus 1, we're going to get the z's factoring out. Q minus 1 over q minus 1 is going to cancel. It's going to be equal to z. So the point where z is on the y equals x line is a point that is on the feed operating line. So I can start at point 3, put my ruler in so I get a nice straight line. And if I've done it correctly, which I've taken extreme care to do, the 3 operating lines should all intersect at the same point. So practically when I'm doing this with graph paper, what I like to do is plot the rectifying section operating line and the feed operating line. And the reason why that is because more oftentimes than R is going to be given as your specification rather than VB. So oftentimes you won't be given what VB is, but R is the parameter that you're more likely to be given. So it's easier to plot the RSOL than the stripping section operating line. And then once you have where the feed operating line intersects with the rectifying section operating line, you can then plot where the intersection is, and you know that that point has to be on the stripping section operating line as well. And then connect that point to where XB crosses the y equals x line. Okay, so now we've got the operating lines plotted. What is next? Now what we can do is step the stages. So I'm going to clean this up a little bit. We are not going to need any of this. Make sure to pause the video now if you need to write down where any of these slopes or lines came from. So another word for stage stepping, or another name for the stage stepping process, is McCabe-Thiele analysis, named after the 2 chemical engineers who came up with it as a graphical means to solve distillation columns. So on the graph, we already know what XD is, so we know where XD is. It's at 0.8. This is equal to XD. We can now use logic to figure out what Y1 ought to be. So on my process flow diagram, Y1, I might have said this earlier, but I know that a total condenser does not change the composition of the stream. So I know that for a total condenser, Y1 is going to be equal to XD. All right, so that means that Y1 is equal to 0.80, and I know that Y1 must be there. All right, so I know that Y1 comes off of stage 1, and if I were doing this algebraically, the next thing I would do is I would say that Y1 is related to X1 with an equilibrium relationship. So what I did when I was solving it algebraically is I said, well, Y1 must be equal to alpha X1 over 1 plus alpha minus 1 times X1. And then when I was solving it algebraically, I had to solve this equation, which was kind of a pain. However, I already have the graphical analysis for it. So when I'm solving this graphically, I know what my Y1 coordinate is. All I have to do is go to my equilibrium curve and find where Y1 intersects that equilibrium curve, and that will tell me what the X coordinate is. So my Y1 coordinate is this horizontal line for 0.8, going all the way over there. And where it intersects the equilibrium curve is going to be right there. So the X coordinate of this intersection is going to be my X1. It's going to be right there. X1 and Y1 are in equilibrium as reflected by the fact that the coordinates Y1, X1 lie on the equilibrium curve. Okay, so I can connect these two with a straight line. That's a straight horizontal line corresponding to solving the equilibrium equation for the X coordinate from the stage above. And in this case, that's the product stream. All right, the next step is going to be, since I now know what X1 is, I can now solve a material balance. So I can say that Y2 is equal to R over R plus 1, X1 plus 1 over R plus 1, XD. And this doesn't look like a material balance, but remember in the previous video, I derived how we got to this in terms of R by starting with an overall material balance. So now that I know what X1 is, I can find the X1 coordinate where I'm on the operating line. So drawing the line is like solving the equations for all values. So where X1 intersects the operating line is right there, and that corresponds to a straight vertical line. All right, now that I know what y2 is, so my y2 coordinate is there. Now that I know what my y2 is, I can now go to the next step, which is I know y2, so now I can calculate what x2 is by equilibrium. And I can go a little bit faster now because I know that y2 has to be on the equilibrium curve, and the coordinate where my x is my x2. So I can keep going like this. And you notice that as I'm going, I'm just alternating horizontal and vertical lines. So this is why it's called stage stepping, is because it starts to look like a staircase a little bit. So horizontal lines are going to be my equilibrium relationships. Horizontal lines. And my material balances, or my operating lines, are going to be my vertical lines. So this is how I can quickly solve for the compositions of the interstage flows. I know what my y1, my y2, my x1, and my x2 are. Now the question that you might have is what happens when you get to the feed stage? So we're now done with stage 2. I can now go on to y3. All right, y3 and x3 are there. Y3, x3 must be in equilibrium. And I need to go one more, right? So down to the operating line would give me my y4. This is coming off of stage 4, which is the feed stage. Now the feed stage, you're going to step the top half off the rectifying section and the bottom half off the stripping section. So this is where I'm going to step over onto the blue line. So if I zoom in now, this bottom leg is going to the blue line, not to the red line. You'll also notice that it happens to be where I step over this point of confluence of the operating lines. That is by design. I designed that for this particular problem, but that corresponds to the feed being in the best place. We'll talk about that more in the coming lectures. But the point is that on the rectifying section, you have to step your stages off the rectifying section. In the stripping section, you have to step your stages off the stripping section operating line. And you can continue with this until you reach what your XB is. And you should find that the number of stages lands directly on XB. So I don't have my lines all the way straight, but I should be pretty close. And now if I count the number of stages, I should equal the number of equilibrium stages in my column. So 1 is corresponding to there, 2, 3, 4, 5, 6, and I have one more. This is going to be the reboiler. So because the reboiler is a partial reboiler, this is in equilibrium and it is counting as a stage. So I have 6 stages in the body of the column and a reboiler, so that means I have 7 steps on my graph. So this is our first introduction to stage stepping. I know that you probably have some questions and it's not all the way clear. Hopefully in the next coming lectures, we'll do some more practice problems and you get the hang of it. The one thing I want to urge you is to never just memorize where to draw the lines on the graph. I mentioned that was my least favorite part of when I was taking separations, is I felt like I just memorized things and I didn't really learn it as well as I should have because I didn't understand what was happening underlying the lines that I was drawing on the graph. So do your best to read the book, watch this lecture multiple times, and really understand why we're drawing the lines that we're drawing, because that will lead to a greater understanding. So thanks for watching. I'll see you in the next video.